I'm going to talk about some basic principles of living systems. We don't know many of them. We're still figuring out a lot of these basic principles as we go. But we know some of them, and I'm going to talk about those. We have basic principles that govern abiotic world, non-living world. We know a lot of them, and we understand quite a bit of that. We don't understand much of what the biotic world is about. What are the basic principles? What are the fundamental principles that govern the biotic world? I'm going to touch upon some of these. Now, have you ever tried to open a potato bag or a seed sack that has its mouth stitched across? Have you ever tried that? It has a special kind of a stitch. And if you got the right end, you pull the string at the end and it unravels quickly. The bag opens. But if you got the wrong end, it doesn't open. You have to find the right end and pull the string, and it opens really, really easily, fast. And you've got this left-right asymmetry in the stitch of the bag. If you got the wrong end, the left side, it doesn't open. If you got the right end, it opens. And with that, my research is about strings of molecules, like beads on a necklace, if you wish, that self-replicate. These molecules existed 4 billion years ago. These are ancestors of the DNA that we have right now. And they floated around in some semi-confined spaces in the primordial oceans. So they had this special property that they could self-replicate, which means you have a single strand, and the single strand helps to form another daughter strand right on top of itself. And once the daughter strand is fully formed, the strands separate. They detach from each other, and then they go on and make more strands. Now, if you want to make this the self-replication evolutionarily successful, it would make sense to make it faster. The faster they replicate, the better they are evolutionarily. Now, how do you think the connections between these two strands should unravel for these double strands to separate into single strands? Exactly like those stitches on the potato bag. Easy from one end, difficult from the other. If you do that, the strands separate very easily, very fast, much faster than the strands that had the same type of unraveling from both ends. That's what we find from our research. And there is an asymmetry built into those strings of molecules. Now, this asymmetry explains quite a lot of things about DNA, right? It explains multiple properties of DNA. You may ask, what if both ends are easier to unravel? Wouldn't that be faster? Why wouldn't that be faster? If it is as easy as it is to unravel one end, if it is more easier, if it is the same as the left hand and the right hand, if they unravel at the same time, at the same speed, wouldn't it be faster? The answer is no. The simple reason is stability. If you're beginning to form the template, the replica stand on the template stand, you're just beginning to build the replica stand. If you make the strand if you make the end of the strand that you began with easier to unravel, then even as you're building the replica strand, the strand's going to unravel. The replica strand is now going to be completely built, and it'll be unraveled even before you complete building of the template strand, of the replica strand. So you need one side, one end of the double strand to be stronger, and the other end to be weaker for it to unzip. So how do you incorporate this? You incorporate this by letting the bonds that form between these double strands, the hydrogen bonds, to influence the left side differently from the right side. The hydrogen bonds would strengthen its left neighbor and weaken its right neighbor. That's the asymmetry. Or vice versa. It should strengthen its right neighbor and weaken its left neighbor. Now, this asymmetry can explain helicity of DNA. How does that work? If the hydrogen bond distinguishes between the left and right by the angle that the neighboring hydrogen bonds make with the hydrogen bond in the middle, then it can distinguish between the left and right, and it can differentiate between them and strengthen one and weaken the other just by the angles. The one on the left is going to make a positive angle, and one on the right is going to make the negative angle, and that's how it differentiates. So helicity can lead to asymmetry. So that's one possible way of implementing asymmetry in DNA strands. And it can also explain, I'm not going to go into the details of it, but it can also explain why DNA is made of 4 nucleotides, G, C, A, T, if you know. And it can also explain why A bonds with T and not with itself, G bonds with C and not with itself. They have to bond with other type of molecules, not with the same type of molecules. And it can also explain something called chirality or handedness. You might have heard of that, that biomolecules have this certain handedness. They are either left-handed or right-handed. DNA, for example, is right-handed. All DNA that is naturally produced is right-handed, and all amino acids or proteins are left-handed. Now you can, of course, you can make left-handed DNA and right-handed proteins in the laboratory, but you cannot incorporate them into cellular machinery. The cell is not going to accept these left-handed DNA and right-handed proteins into its structure, into its function. It's going to discard them. And it's been a mystery why nature should choose one and not the other. Why is it even handed at all in the first place? Why should it use unhanded or symmetric molecules? Why shouldn't it choose that? Now, the answer to this question comes from our research. The asymmetry is the source we find of this handedness. So you have the DNA strand, you have an asymmetry, the left and right are not the same, as I said. Now, if the left and right of the DNA are not the same, the molecules that compose this DNA strand are also asymmetric. The left and right are not the same. And biologists know that you have a 5' and a 3' of DNA. They are different. And now we have an evolutionary reason why they are different. You have to have different left, the left different from the right. And for chirality, if you want to make a double strand, the molecules on the template strand are already directional, and you have another molecule coming in and bonding with the molecules on the template strand to make the daughter strand, and these molecules have to find the right orientation to bond. They can't bond in the opposite sense. They have to bond in the right direction for the daughter strand to form. So for this, chirality is essential. If the molecules are handed, they can find the right orientation. If they are not handed, if they are achiral, if they are symmetric in some sense, they can't form that bond in the right orientation. They can, half of the time they're going to bond in the right direction, but half of the time they would bond in the wrong orientation if they are achiral. So here you have an explanation for why biomolecules have chirality, because it helps in creating the daughter strand with the right orientation, with the right left-right asymmetry. Now, now comes the most interesting part. You all know that water boils at 100 degrees Celsius. What does that mean physically? It means that the bonds between water molecules break and form with equal probability at that temperature. Below the temperature, the forming of the bonds have higher probability. Above the temperature, the breaking of the bonds have higher probability. Now, I've talked about the double strands forming bonds between themselves. If you want to construct a replica strand, you have to form a bond with the molecules for the replica strand forming bonds with the molecules in the template strand. And these bonds also have a certain temperature at which they break and form with equal probability. And that's the melting temperature of those bonds, the hydrogen bonds. So what we did was to set that temperature at some temperature and just run the program. It's a computational program. We just run it and try to look at the replication properties. Curiously, what we found was that the replication took place, the double strands separated well below the temperature, the melting temperature of the hydrogen bonds. The double strands melted into two single strands well below that melting temperature, meaning that the bonds broke even before the melting temperature was reached. This is particularly evident with asymmetric strands. Symmetric strands did not do that as much. Asymmetric strands divided into two, mother and the daughter strands divided are separated well below that set temperature, the melting temperature. How could that be? You have melting even before you reach your melting temperature. Can that happen? Is it physical? Is there something wrong with the program? Now, in a macroscopic world, it's not possible. But in the mesoscopic world, because the thermal fluctuations are much larger compared to the size of the molecule, it's very much possible. So you have these mesoscopic particles, the particles that are very small in size. So they can extract energy from that thermal fluctuation and use that to separate themselves. And that's how they divide even before the melting temperature is reached. They separate even before the melting temperature is reached. Now, this ability to extract energy from the environment, this doesn't happen in the macroscopic systems, but in microscopic systems it is possible. But it's only transient. They extract energy from the environment, but they dump it as soon as they extract that energy. The single strand that extracts energy from the thermal environment, it reunites with its partner and that energy is gone. But in special cases, this energy can be tapped to catalyze reactions, to catalyze conversion of molecules into products, substrates into products. So you have a system here that extracts energy from the environment and uses that to perform reactions on other molecules, to digest other molecules. And when you do that, you create disorder. You convert useful forms of energy in that molecule, in that substrate, into useless energy, entropy. What do you call a system, a physical system, that extracts energy from the environment and converts it into disorder? Isn't that the quintessential characteristic of life, apart from self-replication, that is? In 1940s, Erwin Schrödinger, that's a famous physicist. I don't know how many of you here know him. He's a famous physicist who was instrumental in formation of quantum mechanics and formulating quantum mechanics. He pinned down this as the most fundamental property of a living system, which is the ability to extract energy from the environment and convert it into useless forms of energy, into entropy. And that is the most basic, fundamental property of a living system. And so what we see in our program is just that. Our beats in a string, the molecules in our strand actually do that. by dividing well before the melting temperature, they extract energy from the environment. And now, because with that excess energy, they can catalyze reactions. Now you see the genesis of life itself. Proto-DNA that could both self-replicate and metabolize reactions. This also helps explain why these molecules are small. The DNA, the proteins, all the molecules inside your cellular machinery, ribosomes and everything are small compared to the human scale. They're small because only then they can capture thermal fluctuations, thermal energy to conduct their business. If they are large, if they are like the size of a tennis ball, they can't extract that energy. So you have an answer for why these molecules are small. I have talked about why asymmetric strands, asymmetric ancestors of DNA were better at replication compared to symmetric strands. This reduction of symmetry, or as we physicists call it, symmetry breaking, is also connected in some very fundamental way to fundamental theoretical physics. The whole universe and everything contained in it, all the matter in it, is the result of multiple levels of symmetry breaking. Stars, planets, atoms, electrons, protons, neutrons, everything in the universe is a result of symmetry breaking. That's the fundamental premise of theoretical physics. Even the mass of an object, the m in F equals ma, that is a result of symmetry breaking. You must have heard of Higgs boson. Journalists like to call it God particle. That underlies the symmetry breaking that gives this matter mass. And the distinction between past and future in the macroscopic world, that is also a result of symmetry breaking. At the microscopic world, we don't have that differentiation. The past is the same as the future, but in the macroscopic world, you have past, which is different from future. You can't go back to past. And that is the result of symmetry breaking. It's wonderful to know that the same phenomenon underlies origin of universe and origin of life. That is symmetry breaking. Let me continue with that strand a little further. In the beginning, right after Big Bang, the whole universe was tiny, uniform, no wiggles, very uniform. And as it expanded, it cooled, and it created particles. And that was the first symmetry breaking. And as it expanded, it created multiple levels of symmetry breaking, and it created stars and planets and galaxies and all that. And those are all multiple levels of symmetry breaking. And let me give you an example of symmetry breaking, try to illustrate symmetry breaking. Let's say you have a magnet, and when you heat the magnet, what happens? The magnetic property of the magnet is lost. And when you cool down the magnet again, you regain that magnetic property. The magnetization comes back to the magnet. But the south pole of the magnet after cooling is not going to be the same place as it was before. It could be at the place of the north pole of the magnet. The magnetic poles would have switched. There's a chance of 50-50 chance for the south pole to be in the same place as it was before heating. Now, after heating, there was no magnetization. The magnet is supposed to be symmetric. And after cooling down, the magnetization acquires a direction. There is a directionality there. The left and the right are not the same. in the magnet. And you call that symmetry breaking. And spins inside those, spins of the electrons inside those magnets acquire a certain direction. That is symmetry breaking. Just like the hydrogen bond in our DNA example, strengthening the left bond and weakening the right bond, as opposed to strengthening the right bond and weakening the left bond. They're not the same anymore. These two are energetically they are exactly the same, but nature chose one as opposed to other. Same thing with chirality, same thing with handedness. Nature chose left-handed proteins and right-handed DNA as opposed to left-handed DNA and right-handed proteins. They are exactly the same in terms of energy, but nature chose one of them as opposed to other. That's symmetry breaking. You don't have the symmetry before. It's either left-handed or right-handed. You can't have both. Now, I have illustrated my symmetry breaking with that magnet analogy. I want to continue using the magnet analogy for another important principle of life. Now, I've just told you that magnet is asymmetric. It has a south pole and a north pole. It has a directionality. And let's assume that the magnet points in this direction. You could call it logical 0. And if it points in this direction, you could call it logical 1. And that's exactly how information is stored in computers, in tiny little magnets that point either south or north. If you want to erase that information and create new information, all you have to do is to heat up the magnet and pull it back down. If you want to randomize the information in your magnet, what would you do? That's exactly what you would do. Heat up the magnet, and when you cool down, you've randomized the information in your magnet. It has a chance of 50% chance of pointing to the right and 50% chance of pointing to the left. You've completely randomized it. The information it had before you heated it up is gone. Now, let's map it back to biology. Mutations. Mutation basically erases information in your genome and randomizes it. Exactly as we did with the magnet. It randomizes information in your genome. And mutation is the basis of adaptation of organisms. An organism mutates and creates new information in its system, in its genome, and let the environment choose which information is best suited for that particular environment. That is evolution, basically. Now, if you want to reduce the energy that the system takes for this mutation to happen, you want to place it near something called a twilight zone. Let me go back to the magnet analogy. You want to randomize information in the magnet. You want to keep doing it over and over and over again. Now, what temperature would you choose for the magnet to be in so you can spend less energy in randomizing the information? You want to keep it close to something called a Curie temperature, above which the magnetization has no the magnet has no magnetization, no magnetic property, below which the magnet acquires magnetic property. And that temperature is called what I call a twilight zone temperature. Above twilight zone temperature, the magnet has no magnetization, no magnetic property. Below that, it has magnetic property. If you keep the temperature of the magnet very close to that Curie temperature, very close to that twilight zone temperature, then you can heat up just a little bit, just over the Curie temperature, and lose the magnetization, lose the magnetic property, and then cool just a little bit below that Curie temperature, and you would have randomized that information. So you want the magnet to be at the twilight zone for you to spend as little energy as possible to randomize your information. And similarly, for mutations, if you want to spend as little energy as possible for the mutation, for you to mutate, change with the environment, you would want to be in a twilight zone of sorts, just like the Curie temperature twilight zone. And here we have another fundamental principle of biology. That is that all life exists in some sort of twilight zone. That's one of the fundamental principles again. Or multiple twilight zones, for that matter. It's like being balanced on a knife edge. All cellular components also exist in that twilight zone. DNA, for example, it has to exist both as double strands and a single strand. If it has to replicate, keep replicating over and over again, it has to form the bonds between these two single strands, and it has to break the bonds. The bonds have to be very close to the breaking temperature and forming temperature. If the temperature is too low, the double strand is not going to separate. If the temperature is too high, the bonds are going to be broken and the double strand will never form. It's the same case with fat molecules, proteins, structural molecules, everything. All of them exist in some kind of a twilight zone. And being in the twilight zone is also connected with symmetry breaking, as I've showed you before. So I've outlined quite a few things. I've talked about DNA. I've talked about magnets. I've talked about symmetry, about being in the twilight zone and all that. What connects all these is symmetry breaking. That is the most fundamental thing that unites living and non-living world, and that is symmetry breaking. With that, I end my little talk. Thank you. All right, questions? Sure.
So, can you make life? So you describe life, can you make it?
The question Arturo asks is, can you make life? Certainly not the life as it is, as we know it, but maybe life as I defined it. Life that self-replicates, that extracts energy from the environment, that exists in a twilight zone. Yeah, sure, we can do that, but not right now. We can do that. We can, yeah, certainly. I'm sorry?
Are we doing it?
I don't know. Not yet, maybe. Maybe you should ask that question to Craig Venter. Any more questions? Thank you.